Carrying on from yesterday, yesterday we looked at a very simplified model of growth and decay. Today we're going to expand on it a bit, because we do have to take into account sometimes other conditions. Example, the temperature of an object will never be lower than the temperature of its surrounding. We need to change the equation, and this is how we change it. So the rate of change, the P to T, we still have that constant times P, but we now subtract the constant times N. So we've factorised it there, we end up with constant P minus N. And the solution to this one, there is a trivial case. I mean, if P was just equal to a constant number, it would be a solution. Because if you differentiate a constant, you get 0. And if we were to substitute N in for P, we would get 0. So that's what we call the trivial solution, and it's not a very interesting case to look at. The other solution we're interested in looking at is this one, where P equals N plus AE to the KT. Now if you look at this equation and you think of what we've done with transforming graphs, all we're really saying is it's the same equation as yesterday, AE to the KT, but we've shifted it horizontally. So all we're saying is there's going to be some level that will never go above or below depending on which side of the horizontal asymptote that it is. So P turns out to be the population, that hasn't changed, but the initial population now will be N plus A, because if you substitute in T equals 0, you would get N plus A. K is still our growth or decay, depending on the question constant, and T, of course, is still time. So let's do it via a very old HSC question now, 1993. How long ago is that? That's 30 years? Goodness me, that is an old question. So T is going to be the temperature inside a room. Little t is time. Capital A is the constant outside air temperature. Newton's law of cooling, a typical law that we use in these growth and decay questions, it states that the rate of change of the temperature is proportional to T minus A. Show that this is our solution. Again, it's that one where we don't actually have to find the solution. They're telling us the solution and say, look, show that it satisfies the differential equation. So similar to what we did yesterday, let's differentiate it. It's an unfortunate use of pronumerals when you think about it, because we've got capital T and little t. So what we're actually finding is dt, which sounds weird, but it's the capital T, the little t. Differentiate, that will differentiate A, you get 0. Differentiate A exponential, the K will come out the front. So we get KC e to the KT, but if we rearrange the original equation, we'll get that T minus A is actually C e to the KT. So yes, we do have K times T minus A. So it satisfies our equation. That's fine. The outside air temperature is 5 degrees Celsius. A heating system breaks down. So the indoor temperature then drops from 20 to 17. It takes it half an hour to do that. So after how many hours will that room temperature be 10 degrees? Our equation will be 5 plus C e to the KT. Remember, N was that external condition. It's the horizontal asymptote. And in this question, the outside temperature is 5. So if we were to think of the graph, we would have an exponential graph which will be coming down, its temperature is dropping, but it would go asymptotic to 5 degrees. It will never drop below the outside air temperature. So we get 5 plus CE to the KT. We know initially it's 20, and so C must be 15, because we said that N plus A was going to be the initial temperature in this case. So we have a formula, 5 plus 15e to the KT. We still need to work out what K is though. Some additional information. After half an hour, so 0.5, the temperature is now 17. Substitute that in. We got to solve this exponential equation. We end up, there it is, K equals 2 log 12/15. So we now know what K is. We want to find when has it got to 10. So substitute that in. Now we're making T the subject. Again, I've left it as K rather than writing down that log of all that. But that's K. Bung it all in the calculator and we get 2.46167 approximately. So about 2.5 hours. So after 2.5 hours we've dropped to 10 degrees Celsius. Alright, so they're very similar questions, but now we've got this external condition we have to take into account. We're going to say all it has the effect of is shifting the curve up, or I suppose if it was a negative number, shifting it down.